Hello and welcome. Today we're going to continue our discussion from last time. We are still in chapter 1, functions and graphs, but today we are going to check what have we tackled already. So we have done domain and range already. We already did increasing and decreasing functions. Now for today we're going to have local and absolute extrema and asymptotes and symmetry. So first, we need to tackle what local and absolute extrema is. So, extrema. So, from the word itself, it's from the word it's like the word extreme. So, basically, an extrema are the certain points in the function that is either a maximum or a minimum. So, this is very easy through two ways. We can do this algebraically or with math, or we can do this through graphs or graphical method. Either way, it's going to help you find out which are the extremas of your function. Now with this space over here, let's look at something called the local extrema. First, it's called the minimum or the maximum at a given interval. So let's say we have a function that propagated this graph over here. You can totally see that the function inflects or it changes direction from increasing to decreasing. Then it fluctuates a bit. Then let's look at this part of the graph. This is from the interval 5 to 3. Sorry, negative 5 to negative 3. But let's focus on this peak over here. So this is called a local maximum, and it's at the interval of negative 5 to negative 3. That is called local because you're only focusing on that interval itself, and since it's the highest peak in that interval, that is called the local maximum. Let's look at this other one. This interval from 1 to 3, we can see that there's another dip over there that causes a curve, and we can call that the local minimum, and it's at the interval 1 to 3. So that's called the local minimum because in that particular interval, you can see that there is a dip that's the smallest dip possible in that interval, and we can see that that is the local minimum. Okay. So, absolute extrema is something a little bit different. If you have a local extrema, you're basically saying that that is the highest peak from a certain interval. But for the absolute extrema, you're actually considering the whole function itself, and you're trying to find out which is the minimum or the maximum for that function, which is the true minimum and or maximum of a function, which is of course the absolute extrema. Let's use this example, and let's see, just from the idea we can totally see that from here we can totally see that the absolute maximum is over there, and the absolute minimum is still that lowest point. That is the idea of an extrema. So let's go through an example. So it says here decide whether the function of x is equal to x raised to 4 minus 7x squared plus 6x has any local minima or maxima. Okay, let's find that out. Let's move on. So if you try to use a tool to graph this whole function, or if you try to graph it yourself, you're going to end up with something like this. And you will see that there are some points in the graph where it dips completely, like in this case, as far as y is equal to negative 24, and it can go up again. Okay, so let's look at that highest peak over there, right next to the origin. We can consider that as the local maxima, because that's from this local point in the graph, we can totally say that that is the maximum for that point. We don't know yet if there are still other inflections or other changes in the directions of the graph, but so far from this chunk of the graph, you can totally see that the local maxima is over there at x is equal to 0.456 and y is equal to 1.324. Now you can now see here that the dips can also be called local minima, depending on the interval that you're looking at. But those are the local minima for this kind of function. So it's not really that hard to find as long as you have a tool to graph it or you have a way to graph your function. Then there's always a way for you to find the local and the absolute extremas for your function. So the local extrema is also called the relative extrema. So when you say relative, you're basically relating it to one chunk of the function or the graph. So that's why it says relative. And the other is of course absolute, which is the true minimum or maximum of the function. Let's move on. As for symmetry, symmetry is like art. So the symmetry is the sense of balance in the function. So whether you have a symmetrical function or a symmetrical graph, we have to look at it in such a way that we have a reference axis, which is usually the x or the y axis. Let's go for an example. Let me show you in a bit. Let's start with the basic. Let's start with this parent function for a parabola, which is y is equal to x squared. If we plot this, you will totally see that it's in this form. It's the usual case. And you will notice that for every y that we have two x's. In this case, for every y, we have x and a negative x. We know this because a parabola opens upward in its parent form, and it goes like that until infinity. So the graph looks the same from left and right. So if you try to cut the graph to the left of the y-axis, and compare it to the other cut to the right, they're basically mirror of each other, so they look the same from left and right between the between the y-axis. Now we can say that this graph has symmetry with respect to y-axis. Let's try to tabulate the points here. We can try to analyze this through algebra numerically. So there's a table right here, and we can totally see that in between 1 and 1 over here, there's obviously the 0, which is the origin, and when x is equal to 0, y is 0. Obviously, that's the case. That's the vertex. But the value for f of x repeats after 0, 0. So if you notice from the top, we have 941, and it inverts into 149 after the 0. That is the symmetry that we're looking for, and it's symmetrical with respect to y-axis. All right, so we can also use algebra for this one. So we can assign y is equal to x squared, or we can rename y as a function notation as f of x. Now, in order for us to try to test if there is really a symmetry in between the y-axis, we can try to replace the x with a negative number, or a negative x in this case. The theory is that if you replace the x inside the function with a negative number, it should not change. So let's try to do that. So insert x into the original function, and you will see something like this. So I replace the x squared with a negative x, and you square it. You're still going to end up with x squared, and of course after that you're still going to end up with the same function. So technically we can say that this function is called an even function, because even if you try to change the x into a negative number, or assign a negative number into it, you're still going to end up with the same y, which is of course the description of a parabola, because we already know that a parabola has two x's for every y, and that's what we know. How about this time? This time we have x is equal to y squared. It's now the inverse of it. So let's see what happens when we try to graph this. So let's move. So if you try to graph this, you will find out that this function is a parabola. It's still a parabola, but this time it opens to the right. The difference is that this is actually not a function in terms of y, because of course if you try to do the vertical line test, you're going to end up touching 2 points in the graph, and that's not something that we want. But still, something like this can still happen when we graph, and let's try to analyze what happens here. Now, is this still symmetrical? Let's find out. So just by looking at it, you can see that the graph looks the same from top to bottom. So if you try to split the graph with the x-axis, the top chunk, if you try to mirror it, it's still the same as the bottom, and that's between the x-axis. Now we can see and we can say that this has symmetry with respect to x-axis. And that is true. If you look at it, it's obvious. If you fold it in half, you will find that the top part and the bottom part are basically the same. And if we try to get the values of this is like the opposite of the other one. So numerically, if you try to look at it, from the 0 over there, the numbers inverse, but this time it's not for y. It's now for x. Now for the values for x repeats after 0, 0, so we know that, but it's the inverse now instead of y. And let's move on to another one. This time, let's increase the power of our function. Say this time we have y is equal to x cubed. What do we do with this? So let's graph it first. Let's look at it graphically. You're going to end up with something like this. You can see right away that it could not be symmetrical, but you have to consider that in order for it to be symmetrical, there's still some algebraic techniques you need to put in place. But for this one, well, let's try to test if it's really a symmetrical function. Now let's look at the graph. The graph looks the same from the origin, but this time is the mirror inverse of each other. Now if you try to cut the first quadrant and compare it to the third quadrant over there where the other point lies, you'll see that it's actually the same. It's actually very similar to each other, but it's just negative inverse. Now we can say that this one has symmetry with respect to the origin, because if we try to look at the origin, there's actually a symmetrical distribution of the points from left to right, and that's also considered a symmetry. Let's try to prove this through algebra. Okay, so we have y is equal to x cubed, and numerically, let's look at it. I'm going to take this first chunk of numbers at the top and compare it to the chunk of numbers at the bottom. You can see that the values of x and y become negative of each other. And of course the inverse. If you look at them, you can really see that. They became negative and they became inversed. If you look at that, and if you look at that. And for functions like this, they are symmetrical with the origin, but they become the negative inverse of each other. We call this an odd function. You will notice that the parabola is an even function, and this one is an odd function. You can also kind of predict what's it gonna be just by looking at the highest power of the variable inside the function. For parabola, it's 2. So since it's raised to 2 and it's an even number, it most likely it's going to be an even function. Same goes for this one. Y is equal to x cubed, therefore odd function. Let's go for another one. So check this function for symmetry. Obviously this is going to be a parabola, and let's try to graph it in this tool over here. You can see that it's a parabola opening upwards, and seemingly we can see that the graph appears to have symmetry with respect to the y-axis. If you could look at it, it kind of looks like that. Even though the graph moved down by 3 units, we can still say that this graph or this function is symmetrical with the y-axis, with respect to the y-axis. Let's try to do this through algebra. Let's try to prove it a little bit. So the idea, remember from before, that if you want to find out if there's a symmetry of your function, you gotta do this technique first. First, you have to replace the variables inside the function with a negative number. In this case, it's a negative x. So the function of negative x, if we try to input it into the function, the x squared becomes negative x raised to 2 minus 3. Furthering the equation, we're going to end up with x squared minus 3, and this is still the original function. which means that the function is even and symmetric with respect to the y-axis, and that is true. You can see it from the graph. So that's how you confirm symmetry with algebra. Let's move on with more example. Check this function for symmetry. This one is the g of x is equal to x squared minus 2x minus 2. Let's try to find out. Okay, so obviously this is going to be a parabola, but unlike the other one, this is obviously a parabola that has a vertex somewhere else. It's not really falling on the y-axis anymore. So immediately upon looking at it, you might assume that the function is symmetrical. But in reality, if in terms of the axes, it's not really that case. It says that the graph doesn't seem to be symmetrical to the y-axis or the origin. Even though a parabola technically is symmetrical, it's symmetrical to its axis of symmetry, yes. But in this case, it's not really symmetrical with respect to the y-axis or the origin, only because the vertex moves somewhere else. If your vertex is on the y-axis, then yes, the function will be symmetrical with respect to the y-axis. Now we can say that the function may be neither odd or even, but how do we prove that? We still have to find out if the function is not really odd or even. So let's try to do that. First, we must prove that if we try to put in the negative x into the function, it's not going to be the same as the original function gx. And the other one is that if we replace the variables inside with the negative number, it should not be the same as if we multiplied the whole function by a negative number. Let me show you through math. So first, let's look at this. So this is the first thing we need to do. We're going to replace the variable x with a negative x inside the function. Obviously, this is going to change because even though we have an x squared over there, we have an x, which means that if we put a negative number in there, it's going to change the sign, which in this case, it gives us x squared plus 2x minus 2, which is not the original function g of x. So there it is. So that's one sign. Let's move on. So we need to conclude that this is not equal to g of x, which is yes. That's the case. Next, we need to try this one now. So let's try to multiply the whole function itself by a negative number. So multiplying negative to the whole thing, we're going to end up with negative x squared plus 2x plus 2. And obviously, this is not going to equal g of negative x, which is the one we got before. So just from looking at it, if you try to compare it with that one, we can say that the g of negative x is not equal to negative of gx. So if that's the case, then what can we conclude from this? Okay, so since these two are met, the conditions are met, we can totally say that g of x is neither odd nor even. So that's how we do it. Now let's move on. One part of graphing, and when it comes to looking at the domain and range of a function, you might notice that some functions give you something called an asymptote. An asymptote is basically it's basically just a boundary in our boundaries where some functions never touch. That's basically what it is. Your function will try to move, or will try to get a value the closest it can to the asymptote, but it will never cross it. It will never touch it forever. So let's try to analyze an example over here. So we have f of x is equal to 2x squared over 4 minus x squared. Let's try to graph this. Using a tool, it gave me this beauty. It's really symmetrical. It's really nice. Now, we can see that the graph splits at x is equal to 2 and x is equal to negative 2. Those are the asymptotes over there. And at y is equal to negative 2. That is a horizontal asymptote. Now, we can see that you will notice that the graph will approach y is equal to negative 2, x is equal to 2, and x is equal to negative 2, but they will never cross those values. they can be the closest they can to those values, like say x is equal to 1.99999 until infinity, but it will never be exactly 2. That is the case for asymptotes. So, let's there we have a name for them. The first one is that x2 and y2 over here are called vertical asymptotes, obviously, because, well, they're vertical. The second one is that y is equal to -2 is called a horizontal asymptote, which is obviously, of course, it's flatlined. It's very horizontal. Let's move on to another example. Let me show you something else. Let's analyze. f of x is equal to x over x squared minus x minus 2. Now, if you remember from domain and range, if you try to get the domain and range of your function, it will give you the set of values that's allowable for x and y. The first thing is that you can actually use that idea or that knowledge of domain and range to determine the asymptotes. If we have a fraction like this, it's obvious that we must not have a 0 in the denominator. So let's try to do that. Let's equate the denominator to 0 and try to get the factors of this quadratic function. If you factor it into its components, you're going to end up with x plus 1 times x minus 2 is equal to 0. That's the factored form. Therefore, we have the vertical asymptotes that x is equal to -1 and x is equal to 2. So those are the asymptotes now. But we have another question though. Do we have a horizontal asymptote? That's something that we gotta know. Okay, so it's very similar to what we do for the vertical asymptote. We just have to equate the whole equation to 0, and let's find out what we can get from that. So, if we cross multiply 0 with the terms below in the denominator, you're going to end up with x is equal to 0 multiplied by x squared minus x minus 2, and you're going to have x is equal to 0. Obviously, of course, x is equal to 0 is going to be our asymptote. So it's a resounding yes. Let's try to graph this. If you use a tool, you're going to end up with something like this. We know that we have a vertical asymptote already. So it's these values, x is equal to -1 and x is equal to 2. For the horizontal asymptote, it's actually the whole x-axis itself. So there it is. So the horizontal asymptote is y is equal to 0. And that is how you try to understand and try to determine the local and absolute extremas of a function, the asymptotes, and the symmetry. These are really very basic ideas, and actually these are very important later on in precalculus and calculus. And even though they seem like they're not important right now, you're actually going to revisit these topics and ideas when you try to go to higher math already. So that wraps up our second part of this topic, and I will see you again in the next video, and hope you had a blast.